Because if we go up to the very top, oops, didn't want to do that. If we go up to the very top and look at just this for a minute, we've got a spring of spring constant K attached to a mass M. And right now the system is relaxed and at equilibrium. The energy in the system is 0, the velocity of the system is 0, and the net force in the system is also 0. We're just sitting there at rest. This line represents the equilibrium position. So all harmonic oscillators have some point that's called equilibrium. And when at equilibrium and at rest, the system is not oscillating. It requires some kind of perturbation to the system. You have to displace it or give it energy to start it into motion. And once you start it into motion, then the system begins to oscillate. It's important to understand that we're using the spring mass oscillator as our training point here, because it is an ideal oscillator and it obeys ideal circumstances. The most important of which is that it obeys Hooke's law. All simple harmonic oscillators should at some point or another be shown to obey Hooke's law. So no matter what's causing the oscillation, our oscillators should all look like they have a Hooke's law restoring force. We're going to try and prove that later today, but we're going to start with the Hooke's law force from a spring. So that's the most standard one I can provide. Now, for the rest of this conversation, we're going to start by saying that this moment right here is t equals 0. We're going to pull the object out and release it. Now, before we even start, how much of an oscillation is pictured? We can sit in silence all day. Must there a guess at least? Why a half? Yeah, this is half of an oscillation. So we're seeing only half, because it's going to be redundant, right? We're going to see the same stuff over and over again. So I figured half would be enough to picture. Is that okay with you guys? So you have to understand that we're only talking about what happens till we get to the halfway point, and then everything reverses and we come back to the starting point. So what we're going to talk about only applies to half of the oscillation, because that's all that's pictured. But you can just in your head realize that to get back to where we started, everything we talk about is going to go in the reverse order. Okay? So let's start with right here. What happens at t equals 0? So this is our starting point. And because I'm saying it's t equals 0, somebody or something had to cause an initial displacement. And whatever this initial displacement is, this is the amplitude. It represents how far the object will oscillate. But it is the maximum displacement from equilibrium. That is the definition of amplitude. So whatever we pull this thing out and let go, we are establishing the oscillations, and we are determining what the maximum displacement will be. Now, at this instant, the instant we pull the mass outwards, there is instantaneously a force in this direction. Currently, the force is also at a maximum because the displacement's at a maximum. And that force has to be to the left because our displacement is to the right. So at this moment, we are seeing maximum force. In addition to that, since net force equals ma, and the only force acting on it is the spring, our acceleration is also at a maximum because the force is at a maximum. In fact, we can say ma max has to equal minus kx max. This gives you a way to solve for what A max is going to be. In fact, not hard to do. A max has to be minus k over m x max. All right. One more thing you need to know. Right now, all of our energy is in the form of potential energy, 1/2 k x max squared. This has to equal the total energy of the system. There's no kinetic energy. At this moment, the velocity is 0. So all of the energy is in potential energy, and that has to be the total energy of the system. This is going to remain constant. The energy in a harmonic oscillator is conserved. Right. Whole bunch of stuff there, but at time 0, when you displace the object, acceleration's at a max, forces at a max, displacement's at a max. Velocity 0. That means potential energy is at a maximum. And there is no kinetic energy. Right, we advance to the next thing. The spring has begun to move the object towards equilibrium. The force is getting smaller. So the force is still minus kx, and our acceleration is less because the value of x is less. So these are getting smaller. But the velocity is increasing. So we're now developing a velocity in this direction. All right, it's being sped up. It has an acceleration, so it's starting to speed up. The velocity is in the negative direction because our displacement was positive. The velocity is to the left, so it's got to be negative. But more importantly, we now have kinetic energy equal to 1/2 mv squared. The potential energy is less than it was. The potential energy is now 1/2 kx squared, but x is less than it was. But if we add the kinetic energy and the potential energy together, they'll have to equal the total energy, which is 1/2 kx max squared. The total energy is still the potential energy we had at the beginning. So potential energy is going down, kinetic energy is going up, but they have to equal the total energy we had at the start. That total energy doesn't change. So if you know where you are, you can figure out how fast you're going. If you know how fast you're going, you can figure out where you are. All good so far? Not particularly hard? All right. We make it to equilibrium. The moment we make it to equilibrium, net force equals 0 because F equals minus k times 0. That means the acceleration is also 0. So we are at equilibrium. There's no acceleration, there's no force. Finally, there also is no potential energy. All of that's 0 at equilibrium. Our object is traveling at its fastest, so now V is a maximum. This is as fast as it's going to go. It's going through equilibrium. So our kinetic energy is at a maximum. And that's got to be equal to 1/2 mv max squared. but the energy is conserved. So this has to equal E total, which means it has to equal 1/2 K X max squared. Now, you probably know exactly what I'm going to do next, but we can figure out how fast it's going. We know the energy, we know how the energy works, so we can set 1/2 mv max squared equal to 1/2 k x max squared. Do the math, we'll find that v max equals the square root of k over m x max. If we solve this for v max, we'll get the square root of k over m times x max. That's how fast it's going to be going. Please keep this in the back of your mind. We're going to use it in a few minutes. Now, we're only at equilibrium for an instant, and suddenly we're on the other side, and that means suddenly our displacement is on the negative side of equilibrium. So our displacement becomes negative because it's on the left side. First, that means immediately that the force changes direction. Right, suddenly the force is minus kx. So now the acceleration is negative and is slowing the object down. The object's velocity is still this way, but it's getting smaller because the force and the acceleration are to the right. So this object is now slowing down. Up here it was speeding up. Here it's slowing down. The force is getting bigger, the acceleration is getting bigger, but the object's slowing down. So force and acceleration increasing. This also represents middle again. 1/2 mv squared plus 1/2 kx squared equals, and it all equals either, and keep in mind, it could equal either one of these, 1/2 k x max squared or 1/2 mv max squared. If you have the max velocity, you know how much energy it has. If you have the max displacement, you know how much energy it has. So it can equal either one of those. Whatever one you have is the one you use. Remember, we're slowing down now. Eventually, we'll make it so that we are all the way on the other side at x max now, but now this is negative x max. At this moment, our force is again at a maximum. So force is max. Acceleration is max. Velocity is 0, kinetic energy is 0. We are stopped. All the energy is potential energy. Now, that just means everything's going to start going the other direction now. Right? That force is now at a maximum. It's going to push the object back towards equilibrium. It's going to start speeding up again, and this system repeats itself, and it does this over and over and over and over again. The first biggest takeaway that I need for you to know is that all oscillators are an exchange of energy. They have energy that's oscillating between potential and kinetic. It doesn't matter what kind of oscillator it is. All oscillators have energy that is oscillating between potential and kinetic. So a pendulum, it's going to be gravitational potential. It's still going to be kinetic. So when it passes through equilibrium, it's got kinetic energy. When it's at its maximum displacement, it's got gravitational potential energy. Doesn't matter what type of oscillator we have, the energy is always going between potential energy and kinetic energy. Also, there's guideposts here. Although we started here at t equals 0, what time do you think this is? What part of a period is this? 1/4. This would be 1/4 of the period. This occurs at 1/4 of the period. So going from maximum velocity to maximum displacement is 1/4 of the period. Do you remember every single problem where a car has been stopped by a spring? They can now ask you how long it takes to stop. It will be 1/4 of the period. Or any problem where the object was launched by a spring. They could ask you how long does it take to launch the car, because it's 1/4 of a period. So any problem that involves stopping or starting an object using a spring, it's 1/4 of the period is what it takes to get it started. And it's 1/4 of the period, it's what it takes to get it stopped. Obviously down here, this is 1/2 of the period. I'm talking about the period because you know how to figure out the period for a spring mass oscillator. So from now on, we have methods to deal with that. Everything okay so far? It's a lot of exposition. It's just labels and stuff, but there's clearly a little bit of math inside there. But you now have something that goes with each one of those, right? Do you remember this from Friday? How far did we make it in talking about what these are? Did we get anywhere with these? Did we figure out what they were? What's that? So we did velocity. So can you tell me what it was?
V equals negative V max sine W times C.
All right, so the omega is our generic placeholder for whatever is controlling the oscillation. So although we have K over M right here because we're dealing with the spring mass oscillator, we could write this as omega and it would be just fine. That way, if you know you have a pendulum, you drop in something different. Except we don't need to leave this as V max. You know things, right? What is V max? Look at what we just did and tell me what V max is. Square root of K over M times X max. Yep. That's true. That's what V max is. Or you could write this as omega, and that would be just fine as well. Now, I want to take issue with this a little bit, but are we good to this point? Must also be cosine. And it's got to be the same omega because the peaks are all at the same place. So the thing that controls the period has to be the same. But it looks like every time the displacement's positive, the acceleration's negative. Do you guys see that part okay? So that suggests there's a negative sign out front. Now we could write A max here, but we know what A max is. What is A max? For the spring mass, it's K over M X max, or omega squared. Either one of those is fine. One is generic, applies to all oscillators. One is specific to this oscillator. These represent the motion equations for oscillators. They're really different than the Galileo's ones. They don't have inner stuff that we solve. We can't solve one for the other and plug it in, or we can't list 5 motion variables or 3 motion variables and solve for a fourth. You get this tells you where the object is all the time, but it has limitations. Not to mention what's happening to the object has limitations. Its position's only going between 2 places. Its velocity is only going between 2 values. Its acceleration's only going between 2 values. So there are limitations on what this tells you, but these are the motion equations for a simple harmonic oscillator. And you kind of need to commit them to memory. Now, I do want to, regardless of which oscillator, the period is always going to be equal to 2 pi divided by omega. The frequency is always going to be omega divided by 2 pi. Omega is something physical. It physically controls the oscillation. So all oscillators will have something that deals with position. So position is always going to be something max times the cosine of omega t. The velocity is always going to be minus omega times the max displacement times the sine of omega t. And acceleration is always going to be minus omega squared times the cosine of omega t. This is always going to be true. These are all the things that control the oscillation. What we have to figure out is what is the thing that is causing the restoring force. In order for there to be oscillations, MA has to be equal to minus something times displacement. Whatever this is, this controls the oscillation. This has to be true. This is the thing you're looking for. In any oscillator, you're trying to find the thing that controls the oscillation. Now for the spring, it's K, and everything falls into place. Because what you don't understand, and it's difficult for me to teach this to you, is that whatever you get when you solve this for acceleration, this will always be omega squared, period. So if you can figure out what goes in those parentheses, that will always be omega squared. I want to show you this, okay? This is not going to be easy, and I have 12 minutes to do so. So I want to show you this, but you'll need your calculator, because I have to prove something to you. We pull a pendulum back, release it, the pendulum swings back and forth. We want to see if we can prove what controls the oscillations of a pendulum. We want to see, is there something about acceleration equals minus a constant times displacement? We're looking for this. Mass times acceleration equals a constant times displacement. So I have the mass at the bottom there. It's got a length of L. I want to take a look at how this system behaves. What force causes the pendulum to swing? Gravity. Gravity is acting this way on the pendulum, mg. There's 2 ways to approach a pendulum. I'm going to choose for you. We're going to approach the problem as a net torque problem equals I alpha. So our accelerations are going to be angular accelerations. Our mass is going to be the moment of inertia, and our displacement will be theta. That okay with everybody so far? All right. Is it true that there's an unbalanced torque that acts on a pendulum based on what I've drawn right here? If you remember how that works, torque equals R times F times the sine of an angle. What do you think R is in this case? What is the length of the torque arm? L. What's the force that's acting on the system? What's that? Yep. And the angle that they want is this angle here. Can we agree that that's theta? It's got to be the same as the displacement. Can you see that? They're corresponding angles cut by a transversal. So this has got to be the sine of theta. So this represents the unbalanced torque acting on the system. Now hear me out, this part's hard. The unbalanced torque is this way. That's a rotation that is into the board. The torque is this way. That's a rotation out of the board. So is it okay we put the negative sign here to indicate that the torque is in the opposite direction of the displacement? Is that all okay? Because we need that negative sign. This has to equal I alpha. I is the moment of inertia of a point mass. Do you remember how to find the moment of inertia of a point mass? It's been a long time. The moment of inertia of a point mass is mx squared. What's x in this case? X is the distance from the pivot point to where the point mass is. L. So for us, this will be ml squared. All right. Look closely. This might be hard to see. I need to solve this for the acceleration. When I do, I get minus LMG over ML squared times the sine of theta. This looks super close. This is an acceleration. This is our negative sign. All of this stuff is a constant, right? The length of the string is a constant. The mass is a constant. G is a constant. This, however, isn't a displacement. It's the sign of a displacement. I need it to be a displacement. So we're going to lie. I want to show you a lie, okay? It's only a simple harmonic oscillator if we keep the angles small. So we can replace sine theta with theta if the angles are small. That means this is omega squared. Now, this isn't a surprise. Look at what that is. Cancel out one of the L's, cancel out the M, and you get G over L. It's not a surprise. This is exactly what we'd expect it to be, because we already knew the period and the frequency of a pendulum. This is just where it comes from. It comes from looking at the force and seeing if the force is proportional to the displacement. All right. This part will take a second. So let me write this carefully. Theta in degrees, radians, and the sine of theta. So we have to work fast. I want to do 1 degree, let's do 3 degrees, 5 degrees, 10 degrees, and 20 degrees. Do you know how to convert degrees to radians? If you don't, it's okay. Multiply by pi and divide by 180. So let's do that all real fast. So you guys have 1 and 3. You guys have 5 and 10. I have 20. Convert it to radians. I got mine. This is 0.3489. And make sure you keep some decimals. All right, somebody give me the 5-degree one. Nobody can give me the 5-degree one? 0.087. Give me one more decimal. Somebody give me 3 degrees. And 1 degree.
0.017.
All right. This class, this side, you guys do the sign of 1 degree, 3 degree, 5 degrees, 10 degrees, okay? You guys do the sign of the radian part. They're going to be the same, but let's make sure. I think I'm faster than you guys. Okay. Your chart match my chart? The first thing I want to say to you is, do you notice that when the angle is small, you can't tell the difference between something in radian, the angle in radians, or the sine of the angle in radians? You guys see that? And as the angle gets bigger, they start to get further apart. But even up to 20 degrees, they're pretty close. Other people notice this. It's called the small angle approximation. And it says this: theta is almost equal to sine theta for small angles in radians. That's all it says. That the angle is almost equal to sine of the angle for small angles. This is why when you guys did your lab and you made your angles big, you somehow got that there was something happening, that you thought it might control it. It's because, yeah, it no longer behaves right for big angles. It's not a simple harmonic oscillator for big angles.